Okay, so we have this finite element boundary value problem, and then here we're gonna solve this, and the main objective is to get the stiffness matrix so we can solve this problem. And there are more details that I'm gonna explain, and then this is very interesting problem. And then if you can understand this, then basically you will be able to delve into more advanced finite element problems. So, so we want to solve this, and the first thing usually we want to do is uh, to define the strong form. So in this case, we have U sub double I here plus S equals 0 in domain, and then UG on Dirichlet boundary condition. So this is for Dirichlet. And then here you have uh, sign for Newman boundary conditions. And then we're going to use this later when we apply the divergence theorem. So we want to first develop the strong form of this problem. So we have this two-dimensional domain here 0, 0, 2, 0, 2, 2, 0, 2. And then we have this U apply here equals 1, so there is a displacement here. And then this is the heat flux. No, this is not displacement, this is the U means I'm sorry. This is this is the displacement. I thought it was the heat conduction problem, but actually it's elasticity problem. So yeah. So the first thing we have to perform here is to calculate the strong form here. So because we want to redefine our domain, so this is the domain that we want to solve. So every time you want to solve new element, that meaning that we just want to define our sub element from the entire element, then the first thing we have to do is to redefine the strong form. So as we know here, this is the coordinate is 0, 0.0, and then meaning this is the middle of 0 and 2, so it is 1, 0, and then this is also the same 1, 1, usually because this is 2 at height, and then this is 0 and 1, okay, and then you see this is u equals 1, and then at the right side here you have h equals 2, but because we define this is like symmetry property, so it has to be 0h, and then this is h also becomes 0, and then h here equals to 2. So this is what we have, okay? This is also a symmetry. So we want to develop the strong form, which can be expressed as find u as the solution, such that here u sub I plus s equals 0, where here u equals 1 on boundary 1, so this is the surface 1. So 1, and then 2, 3, and then this is 4, such that u equals 1 and on surface 1, h equals 0 on surface 2, and then h equals 0 on surface 3, and then h equals 2 on surface 4. So this is what we have. So if we cut the domain here, that's because we cut the domain, so these two values are definitely 0. So this is our strong form. Now, what we're gonna do is to perform the weak form. We want to calculate the weak form. Okay, in finite element, we have to construct weak form before we get the stiffness matrices. So how do we calculate the weak form? First, what we need to do is to multiply the constitutive relationship here uh, with wake function, and then we integrate over domain. So this is the over domain equals 0, and then you multiply this. Eventually, you will obtain this one plus here ws here. Sorry, I forgot detail. Here sorry, plus here w s equals 0 here. So what we want to do is to apply integration by part for this. So essentially, integration by part is we want to move these uh, derivatives to the wake function. So that's what we want to do. So integration by part here uh, can be calculated here as follow. So this is the detail about integration by part. I'm going to provide the detail in case you haven't get the idea about what integration by part is. So integration by part can be derived as well from the product rule. So if you set, for example, u here equals to, recall the product rule is d per, sorry. For example, if you want to get the product rule, for example, is like this. Okay, sorry, mumbling. U equals W here, and then P here equals to UI. Okay, so basically you will have UV here. Okay, you want to perform the derivative of UV with respect to I, then this will be U UI here multiply with phi plus U here multiply with phi with respect to I. Okay, so this is what you want to get. And then we replace U with W here. We replace phi with, sorry, UI. And then you will eventually have this. This is plus WI here. Phi is UI. And then plus U is W is U. This is phi. So it's supposed to be double like this. So if you see here W and U sub to I here, then what you're gonna have is this one. Okay, it's pretty similar. So what you want to do is to have this equals to W U here. Sorry, it's to here and then here. Sorry, here equals minus here minus W here U here. Okay, this is what you want. And then you substitute back to this equation. Eventually, you will obtain this equals to uh, is equals to W I here, and then this is I, and then this is yeah, you're gonna have this like multiply with W I and then U I here, okay, and then okay, I forget to put this. I always forget, and then here you have this WS and D here equals 0. So this is what you have after you perform the integration by parts. Now, what you want to do here is to apply divergence theorem to his. So we want to apply divergence theorem Okay, so what is going to happen when you perform divergence theorem? So basically, uh, you're gonna convert this UI, and then you're gonna eliminate this derivation, and then this domain we're gonna change with respect to surface of the problem. So we have this. So sorry. So we have this correct. We have this now. W UI here. UI equals to recall this from this version here. So yeah, UI will U sub A. It will become U sub I multiply with N sub I here. And then this is with respect to the domain of the surface. And then yeah, every and then the rest will be pretty much the same here still. Okay. And then what we have now is we have four surface domain, right? So we want to we want to break this down into one, two, three, and four here, correct? So that's what we're gonna do. And let's see. So we have one here. I can change this. No, this is the same here, and I one, and then plus two W, and I here two here. This is three W U I, and I here three plus here four W UI, and I four here. And then here will be minus the same. And then yeah, it's something that I don't have to write. So if you look at our boundary again, then uh, we have 2 and 3 equals 0. So this is equals to h, and h equals 0. So you can cross this. The same here for 3. And then we have, if we see the domain at 1, we have defined the domain as 1. So basically, we don't need any information for the wave function. So it is also 0. And then for surface 4 here, we have h equals 2, which is the only necessary thing, but we're going to apply it later, like at the very last. So after applying all of those things, we have this 4 W, U, I here, and I, and 4, correct? And then you have this one, W, I here, UI, plus here, WS, D equals 0. So what we want to do is we move this the unknown to the left hand side, so eventually you will obtain this value. Okay, this is our weak form. Finally, okay, it's pretty much simple until this point. Okay, so from now on, this is we can easily define again our weak form as follows. So we want to make, so for weak form we find the solution belong to the trial space function, So such that here U belongs to the H1 Sobolev space when with U equals 1 here, such that here all W or wake function is in the in the functions test space, and then such that here we can have W also belong to the H1 space where when and then W0 on surface 1. So this is what we have. So that's the first thing that you have to put attention. Building the weak form is the heart of finite element, and there is a proof that we can derive to show that the weak form is actually a true representation of strong form. But I won't explain it in this video, maybe in the next video. And then the 3 here, what we're gonna do is to construct the stiffness metric. Okay, this is the fun part. But after you deriving the weak form, actually everything uh, becomes easy afterwards. So usually we're gonna use this Galerkin. Why do we use Galerkin? Because this has not represent the approximation solution, but Galerkin uh, helps us to show that what we want to obtain in our final element value is the approximate solution. So this is exactly what we want to do, correct? So in this case, for example, Galerkin here, we can easily state find UH belong to the function space of the in the solution space or trial space here. So such that all wake function uh, we can state here in the test space. Okay, here so the recall so weak form here and sorry. So if we can recall back our weak form, which is this one here W as for W2 Y2 because H here, okay, this is equal H and H equals 2 at surface 4. So we have 2 here and then this is 4. And then if let equals 0 here and then Galerkin, we will obtain like this here and then here for WH2 or okay, correct. So here, so what we and then after we obtain the Galerkin, now we want to prepare our library. So what does it mean by saying the library? So the library here means that uh, all the variables that we're going to use to solve our equations here. So you have first you have trial. So UH here you have this one is the summation of number of elements. So we have 4 elements here. This is n stands for step function and then the I for nodal value. And then we also have WH here. WH equals to this for and CI. Okay, so this is what we have. And then if you want to get the gradient of del UH here, subspace, and then subscript H, since we have 2 domains here, that means we will obtain I here for NY x di, and then this is for I and y and iy di here. So this is what we have for del UH here. So here we have BD. Okay, so we have to, because this is a two-dimension problem, so you gotta be wary about this. And then for D1, so for D, so we have the same, but we just need to change the notation here. So WH equals to 4 I and IXCI, and then this is 4I and Y and IYCI here, and then this is what we're gonna have, correct? So we can also define our B, or this is B. It's very obvious that B here equals to uh, NIX, okay, and also NI with respect Y, or maybe some reference conveniently mention this way, okay, because they want to make the reader more understand about what they're doing here. But in this case, B also can be decomposed into the Jacobian minus 1 with dn. This is the mapping process, and del n, d eta, and this DLC. Okay, so this is what we have, correct? So we want to break down here into the Jacobian, multiply with the mapping coordinate. So that will be equal to x here, and then when Jacobian multiply with del sub function with del with respect to del eta, then it also will be equal to this, correct? So we know this, but now what we're gonna try to do is to find the Jacobian, correct? So what's the Jacobian? Okay, so we want to find the Jacobian. So we can have the B. Okay, so Jacobian here, right, can be expressed as this follows. So x, del x with respect to C, del y with respect to C, and then del x with respect to eta, del y here, sorry, with respect to eta as well here. So this is the Jacobian. So we need to find this first before we can get the full B function here, correct? And then there are several tools that we're gonna use. The first one is we have to know how to get x and y in mapping condition, in which x here can be obtained by multiplying the set function here, okay, with respect to xi, and then y itself can be obtained by 4I here and y with respect to yi, and then what we have left is the set function which we haven't defined before. So and here this one and 1 and 2 and 3 and n4 here. Okay, and then so n1 here 1 per 4, 1 minus here 1 minus eta, and 2 1 per 4, 1 plus 1 plus c, 1 minus eta, and 3 equals to 1 per 4, 1 plus c, 1 plus eta, and 4 equals to 1 per 4 here, 1 minus eta, minus c, 1 plus eta. And then you might also want to get the derivative of this and sub function. with respect to each map coordinate. So for n with respect to c, you will obtain this minus 1 per 4, 1 here, and then n2 c equals to 1 per 4, 1. You have to perform this derivative by yourself, but so far it's pretty straightforward. 1 per 4, 1 plus eta, 1 per 4 eta equals minus 1 per 4, 1 plus eta. And then here we have with respect to eta, then equals to minus 1 per 4, 1 here, 1 here, minus 1 per 4, 1 plus here, 1 per 4, 1 plus here, 1 4 eta equals 1 per 4, 1 minus c. So we have this. So we want to get the Jacobian value, right? Recall this formula, and so I haven't put this. So what you want to do is to get x. So if you want to get x here, x with respect to c, then it's basically similar concept with ny. So this is eta multiply with x1 coordinate, so xi here. And then if you want to get x with respect to eta, so you just need to multiply the step function here with respect to xi, and this apply with y with respect to c. So you multiply for this one yi, and then y eta, you multiply it for I and I with respect to yi. So this is what we're gonna have. Okay, and then let's find the Jacobian. So find the Jacobian. So here we're gonna have this x force 1. For example, x, this one would be, you have to get this, okay? So x1 e plus n2 here, x2e plus n3 here, x3e plus n4 here, x4e, correct? And then x eta, it's the same. So basically, it's mapping is all about relating our xy coordinate with the derivative of the step function here. So this is n1 eta x2e plus n3 eta x3e plus n4c, I mean n4 eta x4e. So you multiply it with the coordinate. So you already know the coordinate of x here, x1 not here. We have not x1 equals to 0, x2 equals 1, x3 equals 0, and x4 equals 1. And then you also will need to find the y with respect to eta. So it's pretty much y e plus n2 here, y2e, the coordinate n3 here, y3e plus n4 here, y4e, and then y with respect to eta, this one ye plus n2 eta, 2e, n3 eta, y3e, and for eta, y4e. So here you will get the 1 per 2, 0, here 0, 1 per 2. And then the Jacobian can be full, can be write as follow, can be written as follow, 1 per 2. And then if you get the inverse, then you likely get this value for Jacobian. So now you have this already, correct? Now you have this, and uh, once you have this, you can multiply this. So this is our target previously. So this is our what we want to get, right? GP, the B matrix, which is del n, del x here, del n, del y. So this is what we're gonna get, and then so you have BI here equals to 2, which is the inverse of the, then you have this x and y. So this is the B matrix that you want to look for. So BI here equals to this. Eventually you will have this, correct? 2 uh, del n respect to del x, and then here del n with respect to del x. So you have this for BI, which means here, uh, okay, I think it's pretty much clear here. So you need to del n with respect to dx. So you will have to insert uh, the derivative of step function. Have you defined it before? Derivative of step function? No. Yeah, you need to, which is one. I'm gonna continue next video about this.